Let's get going. Today's speaker is Dr. Ryan Anderson. He is from the United States Geological Survey, and he's an expert on, really all things Martian geology, but really he's a rover expert who's worked with, now I think will be his fourth rover, which is pretty amazing. Now, some of you might wonder, what does the USGS have to do with Mars? And perhaps it's not well known that the federal government, most people associate space exploration with NASA, rightfully so, but from the very beginning of US space exploration, there was a recognition that if we were going to do lunar exploration, if we were going to do planetary exploration, you needed to have geologists involved, not just astronomers and physicists and engineers. And so Eugene Shoemaker at the USGS pushed really hard that the astronauts who went to the moon and that be trained in geology, and that geologists from the United States Geological Survey be heavily involved in the geologic mapping of the solar system. And because that is their foremost role in the US, what they normally do in the US. So anyways, the astrogeology department down at the Flagstaff office of the USGS dates back to the earliest days of US space exploration. Has this really rich history, and Ryan Anderson was a Shoemaker Fellow, named after Eugene Shoemaker, right after he got his PhD at Cornell University. I knew Ryan from our days at Cornell. I was a lowly undergraduate. Ryan was a star graduate student working with Jim Bell on the Mars Exploration Rover team. And then he went off to the Flagstaff office as a Shoemaker Fellow, and has since become a USGS scientist there, working heavily with the Curiosity rover, which is still ongoing. Eventually, both the Spirit and Opportunity rovers I guess died, for lack of a better word, but the Curiosity rover is still going strong. And then on next Thursday, on the 18th, we're going to see the Perseverance rover land. So I thought it'd be really apt to have Ryan come and talk to us. The last thing I want to note is that Ryan is a native Michigander, and so we really missed out on the opportunity of having him come home for to tell us in person. So hopefully we can have him back someday. But we're really excited to have him here now. So I'll turn it over to you, Ryan, and tell us all about Perseverance.
All right, Seth, thanks for the great introduction. Yeah, so like Seth said, I am a scientist at USGS in Flagstaff, and I've been involved in rovers since Mars exploration rovers, and it's a super exciting time right now for Martians because we're sending another rover and it's almost there. So let me go ahead and share my screen and we can get started with the presentation. Okay, so I'm just going to give a very high-level overview of the rover, its mission, and then talk about the landing site. Hopefully I've pitched this talk at the right level. I know there's a lot of people from diverse backgrounds here, so I won't get too into the nitty-gritty. And I also want to emphasize that I'll be talking about a lot of different instruments. I'm not an expert in all of them, although I try to know what I'm talking about. So we'll do our best, and hopefully we'll have some time at the end for questions that you may have. So this is a computer rendition of the rover with its robotic arm out. I'll go to the next page, and we'll just talk a little bit about the goals of the mission and NASA's goals here, if it will let me advance. So, the big question for Mars, and the thing that motivates us about Mars, is that right now it is this cold, dry, barren desert. But the more we explore it, the more we find evidence that in the past it had standing water, it had flowing water, it had more friendly weather. The jury's still out whether it looked as wet and nice as the picture on the right here with full-fledged oceans, but we know there were lakes on Mars. We know it was a lot more Earth-like in the past than it is now. And so we want to send rovers to the surface to answer some of these questions that we can't answer from orbit with satellites. And the real science objectives of the Perseverance rover are sort of summarized with this graphic. So there's three main objectives related to sort of understanding the possibility for ancient microbial life. So we want to understand the geology of the landing site. How habitable was it? How much water was involved? How long did that water persist? Was it off and on? Was it consistent? Those sorts of questions. And then an important part about this mission, as opposed to previous missions, is that we are officially looking for evidence of life, astrobiology. The Mars exploration rovers, they were looking for water, not life. And the Curiosity rover was looking for evidence of habitability, but not officially looking for life. So it's this sort of incremental step going from water to habitability to now officially looking for signs of life. Because it's a lot easier to find, the geologic evidence of water than it is to find the geologic evidence of life. And then part three, and then a really important part of this mission is that this mission is going to begin the process of selecting samples to return to Earth. So Perseverance will drive around and cache the samples and deposit them somewhere on the surface for a future mission to pick up and return to Earth. And then finally, this sort of bonus objective on the right is that Perseverance includes some experiments that will help pave the way for sending humans to Mars. And I'll talk a little bit about that later. But it'll collect some data and it has some experiments on board to help with that. So here's another artist rendition of the rover. There's lots and lots of great instruments on board, and I've added some flags to this graphic to indicate instruments that are partly or fully led by teams outside the US. So RIMFAX is a Norwegian instrument. SuperCam, the instrument that I'm involved with, is a joint US, Spain, and France instrument, and META is a Spanish instrument as well. So I'll go through each of these instruments in some detail. Before I get into the individual instruments, I wanted to emphasize in this picture, we have a lot of cameras. The cameras are our eyes on the surface, and they let us see what's going on around the rover. And so it's really important to have a variety of cameras for a variety of purposes. So the rover has navigation cameras and hazard cameras on the front and rear. And new improvement for this mission is that they're going to be high resolution color cameras. In the past, they've been black and white and lower resolution. So even the engineering cameras on this mission are going to be very high quality and usable for science as well. But then on top of that, many of the science instruments have our cameras or have cameras incorporated into them. So we have a total of 23 cameras, some on the rover. There are also some cameras on the landing, the equipment used to land the rover on the surface. And I'll show a video at the very end of how all that will work. But we're going to have some really cool pictures as we are landing, looking back up at the parachute, looking down at the rover, to both just experience the excitement of landing and to collect valuable engineering data for how the landing worked. So now I'll start going through the individual instruments. The first that I'll mention is Mastcam Z. So on the Curiosity mission, there's the Mastcam cameras, and they're sort of the two eyes of the rover. They're mounted right up here at the top. On Curiosity, one eye was sort of zoomed in and one eye was zoomed out, but they were fixed focal lengths. They couldn't adjust their zoom. They were working on these zoom cameras for Curiosity, but they didn't quite get the zoom mechanism working as well as they wanted before Curiosity had to go. So they went with fixed focal length for that, but they used essentially the same design and just figured out that zoom mechanism. So the Mastcam Z is just the successor to Curiosity's Mastcam. And so it'll be able to zoom in and out, which is really nice because we use these cameras a lot to take stereo pictures, and it's a lot easier to do that when both cameras are zoomed into the same level than when one is zoomed in and one is zoomed out. So the bottom here is just an example. You have seen pictures from Mastcam on Curiosity if you've seen pictures from that mission. A lot of the most famous pictures are from Mastcam. They're beautiful cameras. They take wonderful pictures. And so this is just a panorama from a few years ago from that mission. So we're looking forward to having these great cameras on Perseverance as well. SuperCam, as I mentioned, is the instrument that I'm most closely involved with. And again, this is another instrument that is sort of the successor to what was on Curiosity. SuperCam it, like ChemCam on Curiosity, has what's called laser-induced breakdown spectroscopy, which means it uses an infrared laser and it can zap rocks up to 7 meters away from the rover, makes a little spark, and then collects the light from that spark up into the telescope, the same telescope that focuses the laser. And by analyzing that light, we get the spectrum and we can actually tell the elemental composition of the target. So it's a really nice way to rapidly measure rocks at a distance without going through all the time-consuming effort of driving over and touching them with the rover's arm. SuperCam is super because it doesn't just do LIBS, it also does Raman spectroscopy, where instead of blasting the molecules in the rock apart and measuring the atomic emission, it just wiggles them with the laser and measures how the vibrations of the molecules impact the laser light. And so that gives you an idea of what minerals are there rather than what elements are there. And then likewise, it'll have visible and near infrared passive spectroscopy, where we're just looking at sunlight reflecting off the rocks and using that to understand the mineralogy. So between the LIBS, the Raman, and the Vernier, we get a really, really good complete picture of what the rock is made of, much more so than what ChemCam was able to do. And the graphic at the bottom indicates the distance. LIBS goes out to 7 meters, Raman goes a bit farther, 12 meters, and then the spectroscopy and the camera on SuperCam go out as far as you can see, basically. The camera on SuperCam will also be improved as compared to ChemCam. So here's some examples of what ChemCam's camera looks like. So these red dots are where the laser shot across a rock. You can see the scale here is only a handful of millimeters. So this is a very pinpoint targeting on this instrument. The SuperCam camera will be in color rather than these black and white images. And it can be used not only for images like this, where we're documenting where the laser analyzed, but we can also do long distance images. So the top is, these are both ChemCam. The top is a ChemCam that has been colorized using MassCam, but that gives you an idea of what a SuperCam long distance mosaic would look like. And so the high resolution camera is actually serve as a spotting scope. We can look in the distance and get really good detail before we drive up to an outcrop. So that's been fun to use that on ChemCam, and it'll be fun to have a color camera for the Perseverance rover. Next up is Pixel. Pixel is an X-ray fluorescence instrument mounted on the arm. You can see in the little diagram here at the box on the arm. And it measures a spectrum like is shown here. And you can see it detects different chemical elements in the target. But the really powerful thing that sets Pixel apart from its predecessor, which is APXS and the previous rovers, is that instead of measuring sort of a large spot on the target, it measures a very narrow spot, and it can scan across the target and actually put together a map of the elemental composition. So that's what's being shown in the lower right, where depending on what element you're looking at, you can see different parts of this rock lighting up. You can see these little pyrite crystals lighting up in iron and sulfur. You can see zirconium lighting up. They found a zircon in this rock. So it's a really cool instrument. You have to drive up and touch the rock, and it takes some time to collect a map like this, but the information that it can give you is really, really powerful. A related instrument is Sherlock. Sherlock is a UV Raman spectrometer, but it works sort of similar to Pixel, where it can scan across a target with a very small spot size and make maps of what it's seeing. But just like with SuperCam, the Raman is giving you the presence of molecules and minerals rather than the presence of elements. And so on the right is a whole laundry list of the types of molecules that you can see with the Sherlock instrument. And these are actual UV Raman spectra of these. You can see how they look different, and you can understand what you're looking at in a molecular or mineralogical sense. And then to go along with Sherlock, there's an instrument called Watson, of course. So Watson is basically a clone of the MALI camera that is on Curiosity. MALI stands for the Mars Hand Lens Imager. It's basically a color microscope that can take close-up pictures like the one shown on the left. On the left, this is a drill hole that we drilled into Mars with Curiosity. You can see the laser shots from ChemCam shooting down the side of the drill hole wall. And you can see just the resolution of this really nice picture. The other nice thing about this type of camera is that you can reach the rover's arm out and take a selfie of the rover which is valuable for scientific reasons because it gives you the context of where we've done a drill. But it also makes these beautiful selfie pictures that everyone likes to see. This is one of my favorites from the Mojave drill site at Gale Crater, with some beautiful scenery in the background. So between these three instruments that are mounted on the arm, Sherlock, Watson, and Pixel, we get a really, really nice complete picture of a target that we're studying. So this is an example of some stromatolites. So these are fossilized microbial mats. This is probably the most advanced sort of fossil we would expect to find on Mars. We would love it if we saw something like this. But you can see Sherlock and Pixel both make these sort of maps of the minerals or the chemistry of the target, and then Watson provides the image of the target as well. So putting those together, you get a really nice picture of what you're looking at up close. The RIMFAX instrument, this is the Norwegian instrument, and it's a ground penetrating radar. And this is one that I think people don't know as much about, but is really exciting because it will give us that sort of third dimension as we're driving across our landing site and understanding, how different layers of rocks intersect, which one goes under the other one. And it can actually be used as the rover drives. You create these transects across the geology, measuring the layers underneath the surface. And so on the right here, this is a picture of the test model of RIMFAX being driven on the location within that ice. And we'll be able to do a similar thing with the rocks at the Jezero crater landing site. So it's a really exciting addition to the payload. This is something that hasn't been on previous rovers, but it'll really help with understanding the geology. The next instrument is MEDA. This is the Spanish weather station on the rover. And so this will be able to measure the dust optical properties. So how much dust is in the air, how much light is it blocking out, as well as all the usual things you would want to get from a weather station: the wind speed, the direction, the atmospheric pressure, humidity, the air temperature, as well as the ground temperature and the radiation in the environment in several different spectral bands. And so it gives you a nice complete picture of what the environment is like on the surface, which is useful scientifically as well as for planning ahead for humans going to Mars. You want to understand what the radiation environment is like, what the weather is like on a daily up to yearly cycle. You want to understand both the daily variations, when do you get a dust devil blowing across, as well as how do things change slowly over time over the Martian year. And then the next, this is an instrument that is specifically a technology demonstration for planning ahead for human exploration, called MOXIE. And this is an instrument that essentially produces oxygen. It takes in carbon dioxide from the atmosphere and it breaks that down into oxygen and carbon monoxide. And then it measures how much oxygen it has made. And so this sort of technology, if it works as we expect it to, could be used on a much larger scale with a human mission to produce breathable oxygen and oxygen that can be used as rocket fuel. I had a picture of the instrument itself here, but I switched it out for this cool picture from a slide deck that team provided because I love this little this graphic of the spaceman with his MOXIE oxygen. The instrument itself is buried inside the rover. It's just sort of a golden box that sucks in the air and produces oxygen. And another technology demonstration that is going to be on the rover is this little helicopter called Ingenuity. And this is going to be a test of powered flight in the Martian atmosphere, which is a challenging thing to do because the Martian atmosphere is very thin. But here's a very short video showing what that's going to look like. It's this little solar-powered helicopter that will drop from the belly of the rover and then be able to fly around. And it has a tiny, tiny camera, essentially a cell phone camera built in, that can take pictures pointing down and provide context in the area of the rover. Since this is a technology demonstration, it's not clear, for how long is this helicopter going to be flying around near the rover? How long is it going to last? We don't really know. But the main thing is to demonstrate that, yes, we can fly on Mars, we can take pictures and send them back to a rover or another base station. So that'll be a fun technology demonstration, and that'll happen very early in the mission. We want to drop this helicopter and let it do its thing before driving on with the rover and proceeding with the mission. So you should be seeing that relatively soon after landing. So with this huge payload, all these great instruments, we can do a really good job of characterizing the rocks that we are studying. And all of this is, you know, we want to do it for the sake of the science that we can do just through that characterization. But a really important part of it is that we want that data from all these instruments to provide the context for the samples that we collect. So this is sort of a schematic animation where showing how it's going to work. We're going to land, we'll investigate several different locations, collect samples there, and then the samples will be deposited back in one centralized location, or as we'll discuss later, perhaps in two locations, one sort of at the end of the primary mission, and then we might hang on to some samples for an extended mission. But the idea is we measure very, very carefully the area where we collected the samples. We're even going to use the SuperCam laser to mark the top of the samples so that we know their exact orientation once they're drilled up and put into these tubes, so that when we get them back to Earth, we know exactly the orientation they were on Mars to do things like measuring the magnetic fields, the crystals of the sample, and things like that, and orienting those to the planet. So the sampling is a super important part of this mission. It's going to be a big driver of this mission, driving us to move a lot faster than maybe we otherwise would, because we do want to get a big, nice, diverse cache of samples by the end of the primary mission. The primary mission is 1 Mars year, which is just under 2 Earth years. So that's the rover, that's the technology and the instruments that we're going to have. Now I'm going to switch gears and talk about the actual place that we're going. So I'll start with this point perspective of Mars. This is a little bit enhanced. Mars to your eye would look a little bit more drab, but I really like this picture. And unfortunately, the landing site is not centered in this view. It's sort of on the upper edge, but we'll zoom in here and I'll label some of the key landmarks. So Syrtis Major Planum, this is a giant volcanic lava flow area. Very, very distinctive. You can see it in the backyard telescope. It's one of the first features on Mars that was ever detected because it's so dark compared to the surroundings. And then Isidis Basin, this is giant impact basin, very, very old. And Nili Fossae are these giant troughs that are concentric to Isidis Basin, probably formed by that giant impact. And Jezero crater, where we're sending the rover, is right here, sort of in between these very important geologic features. So I'll switch the view. This is a little bit easier to read. This is a topographic view of that area where blue is low and red is high. And so this really highlights the fact that Isidis is this giant hole in the ground. Syrtis is this sort of large, smooth volcanic area. This is actually the volcano here that provided most of the lava. Here are the Nili Fossae troughs. And then Jezero is this crater right on the edge of Isidis. So if we zoom in, this is a roughly true color mosaic of Jezero crater made by a planetary scientist named Justin Cowart, combining a whole bunch of different data sets. It's a really nice view of the crater. And this view is nice because it shows you why, one of the main reasons why Jezero was so interesting and why people wanted to go there. You can see on the left, there's a squiggly line leading into the crater, and on the right, there's another meandering valley leading out of the crater. And so that means that there was water flowing in, but it wasn't just flowing in and evaporating. It was flowing in and it filled the crater up to the point where the water spilled over the eastern rim and formed this outgoing channel. So that means that it wasn't just intermittent, salt pans in the crater. It was filling it up and overflowing the outside. So we know it was a lake at one time. The other reason we know it was a lake at one time is, so here's an artist rendition of what that lake would have looked like, if it was all the way topped up. So we don't think there was a bunch of vegetation or anything. We don't think Mars ever got that advanced in terms of life, but we do know that there was water flowing here. And even if it was icy, it was warm enough to have some water around. So if we zoom in, this is the area where we're actually going to land. And this is a high resolution black and white view of the landing site. And you can see this is a river delta. So that river that goes in, when you have a flowing water that encounters standing water, it slows down that flowing water. It can no longer hold all the mud and sand that's been carrying, so it deposits it as a nice fan. And so our landing site is this circle, this ellipse, and we will land somewhere within this ellipse. Where exactly is unknown. We actually have a contest among the team members to guess the landing spot. Whoever gets closest gets the prize. But it'll land somewhere in here. Most likely, you know, it's a probability distribution, so it'll be most likely in the middle, but there's some likelihood that it'll be out here at the edges. And we have contingencies depending on where in this ellipse we land. But the key is that we want to study this delta. Deltas are super important because all that mud and sand settling out of suspension is really good at trapping any organic life or organic molecules that are in the lake at the time, and it preserves it really well. And so we understand deltas on Earth, we understand the geology, so that gives us a leg up as we start here, and it helps us understand where to look if we want to find that evidence for life. The lowest beds of the delta where the finest grained sediments are deposited, that's where you want to go. And so, you know, these hills out here are probably remnants of that delta, so they might be a good target. The layers at the bottom of the delta are going to be a primary target. And so studying that delta will give us a chance to find these rocks that are preserving evidence of life, as well as a really good handle on the story of water in this crater. You know, how often did it flow? How long did it flow? All of those sorts of questions. The other thing to mention with this picture is that, as Seth said, I'm at the Astrogeology Science Center and for USGS, and we provided this image mosaic as well as a lower resolution image mosaic that will actually be used for the landing. One of the image mosaics is actually on the spacecraft right now, and it is the most precisely aligned map of another planet ever made. And the reason for that is that the rover will actually, as it is landing, it will be comparing what it is seeing with its cameras to our map and steering to avoid, for example, landing on the cliff at the edge of the delta. That would be bad, but landing right next to that cliff would be great, in this nice flat area. And so it will be using the hazard map based on these images from astrogeology to actually steer as it flies down and find a nice, safe landing spot near the center of the ellipse. So that steering capability is new, and it's why we are allowed to have this ellipse that has these giant craters and cliffs inside it. Previously, the ellipse would have had to be out here in the sort of more flat plains, and we would have had a long drive to get to the actual delta. But now we can land right next to it and get started right away. So here's an oblique view. The process of making those maps also means that we have to make very high quality topography, which is another area of expertise at the Astrogeology Science Center. I can't take credit for these products. They're made by the really great product development team. But I really like this view. It shows you the delta in sort of the view you'd get if you were flying in an airplane looking out the window. And you can see, you know, where we're likely to land down here at the toe of the delta, and then where we're going to be driving. We'll drive up onto the delta, and then we'll drive sort of up into the valley and then up into the surrounding terrain in the mountainous terrain outside the crater rim. So here's a slightly different oblique view. This is showing the geologic map that the team put together. We had this fun exercise where we each got little postage stamps of the landing site and had to map them, and then some very brave team members had to stitch all of our individual maps together into one coherent map. So I got to map a couple of the postage stamps right here along the front of the delta, which is exciting. And you know, the whole team participated to make this really, really nice high resolution geologic map, highlighting the different geologic units we expect. So the blue are the delta units. There's this feature up here that might be actually a separate fan or might be an extension, an older extension of this delta. And I'll talk about some of these other units as well. But what I wanted to highlight right now is this area, this dark blue unit. And if you zoom in on it, you'll see why the geologists, especially the sedimentologists on our team, are really excited about this location. We have these beautiful point bar deposits, these curved layers, which are what you get when you have a meandering river channel, meandering back and forth and depositing and then eroding and then depositing and eroding. And so we'll be able to drive the rover right across these, take samples, take close-up pictures, and really put together the story of the fluvial activity, the water activity at this crater, to really get a better understanding of what it was like. And so these deposits are, they're all over the top surface of the fan, and we should be able to get some samples of them and get a really good close-up look of them. So that should be really exciting. So the next few slides, I also want to sort of highlight the mineralogy story. So we have spacecraft around Mars that can take visible near-infrared spectra. And so the next few slides are all going to look like this. These are from the CRISM instruments on the Mars Reconnaissance Orbiter. And these are from a paper that I did with Bryony Horgan and some others a couple of years ago. And so the colors in these pictures are measuring the strength of certain features in the spectrum that are characteristic of certain minerals. So in this map, for example, you can see the delta lights up in green. That's indicating low calcium pyroxene. The blue of the crater floor is more high calcium pyroxene, and then the red in these windows through the crater floor, and then behind the delta, that's olivine and iron-bearing carbonates. And so we can look at the different spectral parameters, and they tell us some different things. So the hydration map, this is measuring features in the spectrum related to water. And the things to note here are the delta itself lights up with some clays as well as some possible hydrated silica. And then behind the delta, you'll see this in several of the maps, there's this bright band of hydration and carbonates that really, really stands out. This shows up in the phyllosilicate or clay map as well. And this band back here is carbonates, the reddish yellow. And then the delta itself, we know, contains clays. And these are probably washed down from up in the watershed. So by studying the delta, we actually get samples of the whole huge watershed that is feeding into this river. And that watershed is cutting into very, very ancient Martian rocks. So we both get to study the delta itself as well as the terrain that it is sourced from. And then this is the carbonate map, and you can see really behind the delta, this bright band of sort of whitish blue stands out. Really, really strong evidence for carbonates. But then also these areas in the crater floor, they're sort of windows through the smoother surface of the crater into a rougher material. These are also containing strong carbonate and olivine signatures. And so it'll be really interesting to drive the rover across those, measure that, and then drive the rover up onto this really, really strong carbonate behind the delta and try to understand the differences. And these carbonates behind the delta are what we call marginal carbonates. And it's possible that they are actually related to the shoreline of the lake. The plot on the right is showing, where certain units in the crater are relative to the elevation. And so the marginal carbonates outlined in red here are the cyan in this histogram. And so they occur between the level of the breach, the overtopping on the eastern side of the crater, and the level that is interpreted to be the highest point that the lake ever reached. So in between those levels is where you would expect sort of the lake shorelines to be, and that's where these marginal carbonates are. And so we think that those carbonates might be tied in some way to the lake itself, and could be a really, really good target for astrobiology, as well as understanding the ancient climate. So they're a high priority target as we drive behind the delta toward the end of the primary mission. And then I should also mention, so the primary mission will take us sort of to the edge of the crater, but we talked a lot, especially as we were deciding on the landing sites, about what do we do with an extended mission? Because these rovers almost inevitably last much longer than their official warranty. The Mars Exploration Rover Opportunity was supposed to last 90 days, and it lasted something like 12 years. These nuclear-powered rovers have a little bit more of a cutoff because their nuclear power source does decay, but Curiosity is still going, and it landed in 2012. So These rovers last a while, and so we wanted to talk about where we would go beyond just in Jezero. And so during the landing site workshop, it was realized over here was a safe landing site as well, and it was possible to drive between them in an extended mission. So Jezero was chosen as the landing site for all the reasons that I just listed, but we have plans to, after the primary mission, we'll drop a cache of samples here, keep some held back, and continue outside the crater and actually take some samples outside the crater out in this area in this very, very ancient terrain, and then deposit a new cache of samples toward the end of an extended mission if we are so lucky to have a rover that lasts that long. So just very briefly, outside of Jezero, you have this whole stack of well-known rocks. We think probably the rover won't be able to reach all of these, but at least these bottom few units up to the mafic cap. Mafic means a lot of iron and magnesium minerals, volcanic minerals. And so we'll at least get the bottom part of the stratigraphy. If in a very extended mission, we might get some of these other ones, but definitely this bottom. And so this mesa here, I think this is a little bit outside the area we'll actually be able to get to, but it shows you there's these mesas with this very clear layers in them that we'll be able to drive across and study. There's also lots of these raised fractures where you have water interacting with these very ancient rocks and forming these ridges that would be really fascinating to study up close. And then one of the really interesting things outside of Jezero is what's called megabreccia. These are giant blocks of material, and they're thought to be big pieces of crust that were thrown up by that giant Isidis impact about 4 billion years ago. And so these are, they're not in place anymore. They've been all jumbled up by that giant impact, but they are still samples of the very most ancient Martian crust. And so being able to get some samples of those would be really fascinating. So there's a lot to do outside of Jezero as well. So this is just a picture of what those samples might look like. We have a large number of sample tubes that we can collect, and we have a pretty clear plan of the types of samples we want to get within Jezero. And then if we're lucky enough to get outside of Jezero and continue the mission, we'll sample a whole wide variety. And I won't go through all these. The point is that we'll get a variety of samples that'll help us answer questions about astrobiology, about water on Mars, as well as things like putting a more firm date on the Isidis impact, on some of the lava flows that we see in the area. Because right now, a lot of the ages of things on Mars are based on samples from the moon, actually, where we can measure in the lab how old those rocks on the moon are, and then go look at the moon and say, okay, how many craters were in that area? And then we extrapolate to Mars and say, okay, we think at Mars, the cratering rate was this compared to the moon. And then we can guess at what the age of these units are. But having actual samples that we can date is one of the really, really important things about sample returns, so we can really nail down the timeline of what happened on Mars. So as I mentioned earlier, we're not returning samples with this mission. We are at the very beginning of a 3-mission campaign to return samples. So Perseverance will drive around, collect this great suite of samples, drop it somewhere on the surface, and then a future mission will come and do a precision landing right next to those samples with a very, very simple rover that will go pick them up, put them in a capsule, and put them on a small rocket that would launch back to Mars orbit. Now that rocket would not be strong enough to launch all the way back to Earth. So it will just put them into orbit, and then another mission after that would come and pick up the capsule and return that capsule to the Earth. So we're at the beginning of what could be a pretty long and involved campaign to get these samples back. But it's exciting to be part of the team that's going to be looking at those rocks and making the decision of what we should sample and what is worth going through all that effort to return to Earth. So I'll finish here with a little video of the landing process that's going to be happening next week. And I'll try to narrate through it as we go. Hopefully you'll all be able to hear the audio of the video as well as my narrations. But yeah, next Thursday, this is all going to be happening. This video is about 3 minutes long. The actual process takes something like 7 minutes. So it's only a little bit slower than what this video depicts. So first, the spacecraft will approach Mars and orient itself just right, and then it'll release its solar panels. It no longer needs those. It's running on its internal power now. And as it approaches Mars, the heat shield will start to heat up. firing these little jets to make sure it's oriented right and go streaking across the Martian sky like a meteor, but hopefully not burning all the way up. This is just showing the view inside the capsule. It's going to be a little bit jittery, but hopefully not too hot in there. And then as it approaches Jezero crater, no longer burning up, fire the big parachute. This will slow it down a lot, but the Martian atmosphere is still pretty thin, so we're still going several hundred miles per hour on that parachute. And as the capsule gets closer to the surface, it'll drop the heat shield away. The heat shield will fall somewhere in the landing site. And then we drop the rover. The rover actually slides down on this sort of jetpack with the rover underneath. And this is the point where it's comparing those images made by USGS to what it's seeing on the ground and steering to a safe location. Eventually it'll get close enough to the surface, find a nice flat spot to land in, stabilize, and then the rover gets lowered down on cables, touches down on its wheels, cables get cut, and then the sky crane, the jetpack, uses up all the rest of its fuel, flying as far away as possible because we don't want it to crash on top of our rover. And so that'll go crash somewhere, and then the rover will wake up and be able to do its job. So the last few seconds of this video are just slowly zooming out away from the rover to just give you a sense of scale. This is using the real topography of the landing site. So this is what the front of the delta is going to look like. And there's our tiny, tiny little rover ready to explore this huge delta and eventually get up into these hills that are the crater rim. So it's really exciting. All of that happens autonomously. The time for the signal from Mars to get back to Earth is something like 11 minutes right now. So and since it only takes 7 minutes to land, we can't control what the rover is doing. That all happens automatically. So everyone, even the engineers who built that system, are just going to be sitting and waiting and hoping that everything goes well. We have confidence that it will. It went well with Curiosity, and we've only improved from there. So I'm not too worried about it, but it's still going to be, I'll feel a lot better once it all happens and we're safely on the ground. So that's the end of my presentation. Please do follow along with the mission. The social media team for the mission is really great. They share lots of good stuff. So you can follow along there. You can check out the websites. But it should be really exciting. It's the beginning of a big campaign to return these samples to Earth. And the science that this mission can do is really great, and it's a really, really interesting landing site. So I'm excited to see it from the ground after staring at it from orbit for so long. And so, yeah, tune in and follow along. And with that, I will start taking some questions.
Awesome. Thank you very much, Ryan. That was a great overview of the mission, and really piqued my excitement and interest for the landing on Thursday. We already have some questions. I'm going to turn on Leanne's, approve Leanne so she can ask her question herself if she wants to, and then we'll go from there.
Can you hear me?
Yes.
Yes.
Yeah, I just had a question about, you mentioned that you guys were, I don't remember if you said it was going to be able to be measured on the rover or when you get the samples back, about looking at the paleomagnetism of some of the samples.
Mm-hmm.
And I guess I was just wondering, in the absence of a magnetic field, what kind of information do we think we can get from those kinds of analyses?
Yeah, so I'll admit I'm not an expert on this, but it's going to be with the return samples. It's not something that we can do with the rover. But there are areas of Mars that do have a remnant magnetic field in the rocks that we can detect from orbit. That's mostly in the southern hemisphere, and this is in the northern hemisphere. But the thought is that Mars did have a magnetic field at one point, and it has gone away. But it's possible that we could see something in these ancient rocks. And another thing that we look for is biomineralization. So magnetite can be produced by life. So it's not exactly the same, but identifying magnetite would help us and may serve as a biosignature as well.
Cool, thank you.
Hey, Brian, do you want to ask your question?
Sure. I was just curious on the ground penetrating radar. How deep does that look? Or how deep can it look?
I would be guessing if I answered that. I don't really know. I think I actually don't know. I would guess 10 meters, but I really think it depends on you know, what kind of rocks we're encountering. And I'm not an expert in that technique, so I'm not really sure. Sorry.
Thanks.
So we another question was posed by Michael Velbo, who I wanted to say at the end of Brian's talk that Michael will be offering a second round of Perseverance, a second talk on Perseverance rover in 2 weeks from now. So please, everyone, come back in 2 weeks, same bat time, same bat channel, to hear him speak. But he has a question for our speaker, Ryan. So go ahead, Michael.
Thank you, Zeth. Ryan, great talk. Enjoyed it immensely.
Thanks.
I guess I have maybe 2 questions. The first one, you mentioned something about the pace of work and motion for Perseverance. Since we don't know specifically where in the landing ellipse it's going to wind up, there are scenarios for notional traverses. If it lands here, how will it get to the delta? If it lands there, how will it get to the delta? But overall, within that range of options for the notional traverse length for the primary mission, how long, what is the length of the traverse pace through Jezero crater, the primary mission traverse length, and how does that compare with Curiosity's traverse distance so far?
That's a good question. I haven't actually sat down and measured out what the length of the traverse would be. I think the landing ellipse is something like 7 kilometers across. And so a traverse, you know, you can imagine if we landed at the east end of that ellipse and we wanted to get, you know, past the west end, it's probably going to be in the 10 to 15 kilometer range once you account for zigging and zagging and stopping at different waypoints. And so that is, I think that's, I'm trying to remember how far Curiosity has gone. That's shorter than we've gone, but we've been on the surface a lot longer with Curiosity than the primary mission of Perseverance. So Perseverance will be able to drive farther autonomously than Curiosity. I know they've done a lot of improvements on that. So I think they're pretty optimistic about making moving along at a pretty good clip for a rover when we're not stopped and studying a specific location. So we hope it's doable. I know they're going to be pushing very hard for us to get all those samples, get a cache of at least, I think, 20 samples is the goal within the primary mission. But it's going to be a pretty fast cadence compared to what we're used to on Curiosity.
Cool. My follow-up question is that you've had experience now. This will be the 4th rover you've worked on, right?
Yeah.
With all the practice and training preparation that you've been involved in for this one, can you say a little bit about how you expect your experience to be different from the previous missions, any or all of the previous missions you've been on, by virtue of the fact that a certain amount of extra work to collect samples is going to be part of what's going to have to be done on this one, which I presume affects how long you stay in one place and what the pace is. How do you expect your work to be different?
Well, I guess the first answer is it's going to be very different in that we will not be all together at the beginning of the mission living on Mars time. We're all going to be separate, and I have young kids now and I didn't before, so I'm not going to be doing Mars time really. I might get up in the middle of the night to do a shift now and then, but we won't be, a lot of us won't be living on that Mars clock like we did before. So That'll be a little bit different, but more generally, I think, like I said, it's going to just feel a lot more fast-paced. We've been practicing and practicing, trying to find efficiencies wherever we can so that we can get the planning for the day done quickly so that we can maximize what we're doing, but at the same time, just get a move on, keep moving. That's been a problem with Curiosity. Not really a problem. It's been, we've found a lot of great things, done a lot of great science by going slowly with Curiosity, going more slowly than we originally planned. But that we won't have that luxury with this mission. We've got to get to the edge of the crater because we have to get there to get all of the samples that we need for a diverse sample cache. And so it's just going to feel a lot more fast-paced, I think. It's going to be the big difference.
So if I'm understanding correctly, it's both the distance that has to be covered to get through the Jezero crater sample area, but also different because of improved efficiencies in the work process relative to Curiosity?
Right. The actual day-to-day planning, we found some efficiencies. There's a certain amount you just have to do by hand, and it takes some time. But then the rover itself is going to be more capable in terms of autonomous driving. So we'll be able to go farther between stops, basically, especially when it's a nice open flat surface, like at the beginning, if we land on the crater floor. We'll be able to go quite a bit farther than previous rovers have been able to go.
Terrific. Ryan, thank you very much. Great talk. And good luck next week.
Thanks.
All right. Thanks, Ryan. Danita had a question for you as well. So Danita, please ask your question.
Sure. Ryan, great talk. I love the graphics. It's just amazing how we could image a place so far away like that. It's my understanding it's crowded up there right now with 3 missions that are jockeying for space. This isn't really a geology question, but as a layperson to it, who is there traffic control? In other words, is there some sort of cooperation, international agreement or cooperation? We're all aiming for the same target. In Antarctica, we have treaties governing what goes on down there. Do we have agreements governing Mars?
That's a good question. I don't know exactly. It seems crowded with 3 missions showing up at the same time, but space is big. It's not going to be a problem. And I think, I don't know to the extent that the Chinese and the UAE and the US are formally communicating and saying, hey, we're going to be at this point in the orbit at this time. But the orbits are measurable. Anyone can see the orbits and see where the spacecraft are. So if that were to be a problem, I think we would know it and be able to adjust. But space, like someone commented, space is big. It's really not going to be a problem. It gets to be a problem around the Earth, where we have a lot of debris and a lot of dead satellites and things flying around. Mars, we haven't messed up too much yet, so it shouldn't be too much of a problem.
Well, speaking of not messing up Mars, I know a big concern that NASA worries about a lot is contamination, contaminating that biological signal. Are the other space efforts, are they as concerned? Again, I would look for international agreement on what we're trying to do up there. But
yeah, I'm not super involved in planetary protection, which is sort of the name that we give to that effort. I know different countries have different sort of feelings about that. I don't know so China's mission that just went into orbit, they have a rover that they're going to be landing in a couple months. I don't know to what level they've sterilized that. I know Perseverance, most of the rover is somewhat sterilized, and then the actual hardware that's going to contact the samples has been like super like as clean as we can make it. But yeah, it's tricky. There are some guidelines set down. NASA has a planetary protection guidelines, but I don't think there's any law in place that can force other countries to follow those guidelines. So we'll see. Again, Mars is a pretty big place, so a rover in one spot is hopefully not going to contaminate a landing site in a different spot.
Let's hope so. Thank you. Thanks so much.
Before we get to another live question, we have an anonymous question. So I'll just read it. With the Mars atmosphere being so thin, how has the Ingenuity helicopter been designed or tested on Earth to account for this difference in atmosphere?
Oh, how did they test it on Earth? Again, I'm not an engineer, so I don't know exactly. I know that they test like the parachutes in wind tunnels that have been pumped down to their correct pressure or at very, very high elevation, like from an airplane, like 40,000, 50,000, 60,000 feet, wherever the pressure is appropriate. I know they've tested the landing system, the parachute at those pressures. I don't know to what extent they've done that with the helicopter. I would imagine they at least tested it in a pumped down vacuum chamber where it can lift off and prove that their calculations were right and that those rotors are good enough. I think it has something like 4-foot wide rotors, and the actual helicopter is like this big. So you need a really big rotor to lift even a small payload because of the thin atmosphere. But I don't know the exact details of the testing process.
Huh. Well, it'll be pretty cool if we start sending hovers instead of rovers,
right,
in the future. Okay, so Dalton had a question, so I'll let him ask his question.
Okay.
Yeah, in one of the earlier slides when you're showing the mineral maps of the crater surface, and maybe I misread it, but it looked like there was maybe some significant deposits with olivine, like within the crater near the delta.
Mm-hmm.
I was curious if I was reading that right, if that implies that there's been some volcanic activity since the lake is drained, or if that's a remnant of the bedrock of the lake, of the crater that then formed the lake itself. I guess I just didn't expect olivine to survive through the weathering directly at the surface if there was significant water, but maybe I'm just interested in that.
Yeah, so that's a great observation, and that's one of the sort of puzzling things about Mars. It's a very volcanic planet, but it also had a lot of water activity. But we see olivine all over the place. There's a lot of dark sand dunes that have a lot of olivine grains in them, and the units that you saw in those maps, those are crater fill. We don't see the original floor of the crater. It's all been buried by either sediments or volcanic activity. And the jury's sort of out on what those floor deposits are, whether they are directly volcanic, are they a lava flow or an ash deposit, or are they just eroded volcanic rocks that have been deposited as sediments, but the water wasn't present long enough to alter the olivine to clays or something else. So that's part of the question. The olivine that in the crater floor does coincide with a lot of carbonate. And so there may be some alteration going on there, and there is clay present. But you're right, there's a pretty strong olivine signal. So it's still sort of a mystery about how does that match up with a long-lived lake? And maybe the lake wasn't as long-lived as we thought. Maybe this surface was protected from the waters of the lake somewhat and has been exposed since, and it's been eroded away. We're not really sure, but we'll see. But yeah, the question of olivine is a tricky one for Mars because you would expect it to alter pretty quickly if it was wet for a long time.
Thank you. Yeah, really fascinating.
All right, so let's finish up with a question from Gabriel. So you can go ahead and ask your question, Gabe.
Hi, thanks for the presentation. I really enjoyed it. I had a couple more basic questions about Ingenuity. I was wondering, because of the time delay, obviously all of it has to be autonomous. So I was wondering how that's going to work and how you pre-plan those flights. If the primary purpose is demonstrating flight in the Martian atmosphere, what's the long-term goal of that? Is that future hover missions? Just wondering a little more about the purpose of Ingenuity, and if we're going to get really cool drone videos of the surface of Mars from that device.
Yeah, so in terms of the planning, I expect it'll be similar to the rover, where we don't command it in real time. We give it a set of commands, and then it executes them, and then it sends back the results. I imagine the helicopter, the commands will just be like, fly up 10 meters and fly forward 30 meters and then land. And then it will communicate with the rover will communicate with the orbiter, and the orbiter will communicate back to Earth. So I don't know anything more about the details of how they'll plan the actual activities of Ingenuity. And then of course it'll take pictures. And I don't think it takes video. I don't think it's that advanced. It's essentially a cell phone camera strapped to a helicopter. So I think we'll get some still images while it's flying. But Ingenuity was sort of added to the mission late in the process, and the science team was not very involved. So I don't know a lot of the details about it. So I'm not really sure what to expect. Hopefully it'll provide some cool pictures. And then, you know, for future missions, I think the idea is, you know, could we do a dedicated helicopter mission that has a more sophisticated payload that's more capable? I think it'd still have to be a pretty small spacecraft, but it might open up some interesting opportunities that you couldn't do with a rover.
Thank you.
Yeah.
Super cool. Yeah, the site that I always want, well, now I'm blanking on its name, but that giant canyon system on Mars,
Yeah.
really where I would love to see visited, and maybe a helicopter is the right way to do it. I mean, like a Grand Canyon tour, really just fly down the length of it.
Yeah, Valles Marineris is great. And every time we look at landing sites, there's some landing sites sort of on the flanks of Valles Marineris that are really, really fascinating, but they're never quite safe enough. I think the winds on the edge of the canyon are pretty bad, and those sites are pretty rough. So maybe as we get better at landing, we'll be able to go there. But as you saw, the plan for the next few missions is to be focused on returning samples. So we may have to wait a little while for a Valles Marineris rover or helicopter.
Yeah, let's go for that helicopter. Okay, so thank you again, Ryan. I'll provide some applause, but it was great talk. And hopefully we can have you back in person at some point.
Yeah, it'd be great to be back in Michigan at some point.
Yeah, and I do have a recording of this talk. So, and I'm going to send it to Ryan. So you can either come to me or to Ryan if you'd like a copy. All right, thank you.